What's up, guys and girls, whoever may be listening to this at the moment? This is Night Chemistry, Acids and Bases 1, and we're going to dive right in, get you caught up. This follows right on the heels of the solutions unit, and it's really just kind of a deep dive into a special solution. We'll look at that here more in a moment, but without further ado, let's get straight to where we go. Without further ado, anyway, here we go. We're going to start off like we often do on a do now slide. Where we're going to talk about, just kind of an intro level, inquiry-based scenario into studying the unit. Sorry, my jacket's like showing up on this little transparent part. Anyway, so we're talking about acids and bases, and the best way to do this is actually to get on board with some of the naming rules that have changed, that are different for acids over and above our normal rules. So essentially, we had old rules on naming all compounds. Well, acids get special naming privileges, and there are a couple of these to look at. So what I do is actually start off everyone with this worksheet. It says on the do now for the roll top desk. And this is actually on one side is the naming rules, and on the other side is what's called the scavenger hunt. And the scavenger hunt worksheet actually just asks some questions of the students, and you answer them in your own pen, and then you end up asking others. You answer about 4 of them is what I end up tasking with. But I'll get back to that in a second. On the other side of the back is this conjugate practice, which we get into via the notes. Okay, but like I said, it starts off with the naming of acids because there's just different enough to have your own set of rules worth taking a mention at. And so it's a little bit different than what it was in person. If you're watching this, I've updated it just to include some instructions, kind of let you go about it more on your own. It is sort of self-explanatory. I've always found in the past that maybe 1/3 of students require some extra attention to it, and that's not anything against the student. It's just generally speaking, I think if anyone spent enough time with it, they'd understand that there's a flow to it and the pattern to it, and it kind of self-teaches you. Nevertheless, there are rules for naming acids. They're new yet similar to the former ways of naming any other compound, which is why we actually named them in this worksheet by looking at the old name next to the new name. And it takes into account the former ways, and then we practice applying new rules for naming acids. So acids and bases, new unit, task first with looking at how to name an acid. You may have seen this before because we've seen things like phosphoric acid and sulfuric acid and hydrochloric acid and all these other compounds, and you've had to ask me what the formula was, and I told it to you, especially in terms of doing the chemical reactions and stoichiometric conversions. So those that's where those come from. Anyway, let's just go right into it. So for each problem below, numbered 1, 2, 1, 2, 3, okay, below the rule, so it says rule and then the numbers. In this top section only, we're going to apply the rules. Applying the rules begins with writing the chemical formula, the compound name based on the formula formerly learned method for naming chemical compounds, and the acid's real name, which is just a new, more precise, based on the new rule introduced. Seeing the example is probably the best thing to look at first, where it says EXE, colon, and then whatever it says after that. Under each rule to guide you in what to include. Plus, one of these 3 is already provided, so you just need to do the other 2 parts. You'll see in the example what I'm talking about. So in the example, it shows, I'm going to skip the rule for a second because the rule we just apply to each of the different scenarios. So in this example, it says HCl, that's the chemical formula. Then it says the old rule's name. We would call that hydrogen chloride by the old rules. And then the new rules, we have to look at the rule to actually apply the rule. So if we would call it hydrogen chloride, plugging that into the rule, hydrogen chloride, if chlor were plugged into the blank here, chlor would be the blank situation that's part of this rule. Chlor is the carryover from the old naming rule to the new naming rule. Okay, that root. So what we fill in the blank here, chlor, we would also fill in the blank over here. Oops, I don't want to get rid of it. Okay. So we're going to fill in that blank right here. So it's chloride becomes hydrochloric acid. Once again, this begins the new rule, the name of the new rule. So that we would say HCl is the formula. Old way we'd name that is hydrogen chloride. Bring over the chlor and call it hydrochloric acid. So the rule is bring hydro, bring ic. When do you do that? When the old name is hydrogen blankide. So let's look at the next one. Let's look at number 1. It says hydrogen bromide. Notice how I emphasize that. Old formula would just be H, B, R. Of course, Br has a -1 charge, H has a positive charge, so they reduce, so just ones. That's the old way we would formulate it, and we'd call it hydrogen bromide. So let's plug that into the rule. Hydrogen bromide becomes hydrobromic acid. Hydrobromic acid. That's it. Number 2, HCN. So we look at the back of our periodic table and we find that on the back there, CN, not CN2, just CN, is called, cyanide. So we would call this old rules. We have the chemical formula already. So old rules, we would call that hydrogen cyanide. Hydrogen cyanide. Plugging that into the rule, hydrogen cyanide becomes hydrocyanic acid. So the third name, we would call it hydrogen cyanide, and the third thing we have to do is hydrocyanic acid. Pretty straightforward. Go back and replay that if you need to. Hydrofluoric acid. Now this gives us the third name. We have to provide the old name and the formula. Hydrofluoric acid is hydrofluoric acid, so it would become hydrogen fluoride. Okay, hydrogen fluoride. That's HF. Any questions here? Send them to me if you got them. Or try it out and then send me what you got. That's probably your best bet. Okay, and that's all for any compounds where the old name was hydrogen blankide. Rule 2 is where the old name would be hydrogen blankate. It becomes, we don't have a hydro now, it becomes blankic acid. So hydroblankate becomes blankic acid. Example, HClO3, old way would be hydrogen chlorate, because ClO3 is chlorate ion and hydrogen is H. So hydrogen chlorate. It ends in 8, so we look at this rule because it ends in 8. Take the root chlor and make it was hydrogen chlorate becomes chloric acid. Get it? The next one, you try it, and I'll tell you in a second. Coming back to it, I want to look down at, well, anyway, I'll do the first one with you. Hydrogen borate. Hydrogen borate becomes bor, carry the blank over, ic acid. So it's just boric acid. And the formula for hydrogen borate is H, and BO3 is borate ion. Don't forget to crisscross. Borate brings a 3 minus, so it should bring right there H3BO3 is what the formula should be. And that way we provided all 3. Good? I think so. That's where any of the old names would be called hydrogen. If it would be called hydrogen borate or hydrogen blankate, it becomes blankic acid. Rule 3, also similar, is anything that we would have called hydrogen blankite, so ite ending, becomes blancus acid. So HNO2 would normally be hydrogen nitrite. So nitr carries over, so it's hydrogen, so it becomes nitrous acid. Cool. Let's look at the first one together here. This is hydrogen chlorite. That's HClO2 as the formula. And the way we'd name it, a hydrogen chlorite becomes chlorous acid. But don't be confused with number 2 here. HClO, ClO on the back of our periodic table says is hypochlorite. So the old way we'd name number 2 is hydrogen hypochlorite. Hydrogen, no, we're down here. Hydrogen hypochlorite. Because ClO is hypochlorite, that's the name of the ion. So hydrogen hypochlorite becomes hypochlorous acid. Whatever's in that blank. Hypochlor was in that blank, so it translates over to hypochlorous. And that's it, folks. Not difficult there. The only difference is with sulfur and phosphorus. Whenever we changed their old names, we'd say hydrogen sulfide instead of sulfuride, or hydrogen phosphide instead of phosphoride. You just make them long again. So sulfur becomes sulfur, and phos becomes phosphor. You can see it here. Add the back to sulf, add the or back to phos. Get H2SO4 instead of hydrogen sulfate or sulfic acid, make it sulfuric acid. I don't know why they did it. Notice you can see hydrophosphoric and sulfuric. You can see it there too. All right, then for the bottom section, that completes the top. Once you finish all 3 of those, of course, you can send me your questions. Make sure you got it, doing it right. For the bottom section is, I want to practice only the new naming system. So you can list the old name way just to reference it if you want to, just to be consistent with the 3 parts to it. But in this next set, I actually just want either the new name, the new acid naming rules name, or the formula, whichever is not provided. So I just need 2 of the original 3. Basically, I don't need the old name written for the answer. So look at number 1, it's H3BO3. I can say the old name to myself. That's hydrogen borate. But I just want to know hydrogen borate means I look at rule 2. Hydrogen borate becomes boric acid. And so it has the formula. I just need to write the new name, and I'm just going to write boric acid. Acid. You get it. You follow what I'm getting at right now? So remember, if it gives me the formula, I write the new name, not the old name. I can say it, I can include it, but I don't need it. It's not required. Number 2, or if it gives me the name, the new name, I want to write the formula. So hydrochloric acid, oh yeah, hydrochloric means look at the rule 1, because that's the hydro blanket. So I would have called that hydrogen chloride. So the formula for hydrogen chloride is HCl, and that's number 2. Finish that worksheet, send me what you got, let me know, and we'll go on from there. All right, and that takes us to the board notes. I gave students enough time to finish that, really more than enough time. Probably about as much time as I spent going through it right there is about half the time that they got in class. Anyway, so about, I don't know, 15, 20, 30 minutes, something like that. Anyway, and then I dove right into some board notes about acids and bases. We just read right through it. I already posted these as a board notes to the unit part, to this unit first posting, but I just go into greater detail, and I'm about to in the video as well. So acids and bases are really just special solutions. Okay, that's all they are. Remember the dissolving process. You know, solutions, they dissolve, where you have the solvent surrounds ions of the solute. It's the best way to see it is in terms of polar molecules. So we said sodium and chlorine were being dissolved by the opposite charged ends of water. So you can notice it here. Na and Cl's are surrounded by oxygens. You can kind of note that right here and here. They're surrounded by waters. And I even put the part of the waters written so that you can see which part of the thing actually goes around it. Okay. So what if we take another special salt, you know, because solutions are just salts dissolved in water a lot of times, most of the times that we looked at it. Let's take a salt, HCl in this case. HCl in water, let's imagine H is the positive charge and Cl is the minus charge. You might expect something similar because it's a solution. But it's a special solution in so much that the hydrogens are so little and have such a capacity that they don't need to be surrounded. They don't separate so much so that they're surrounded by water, oxygen molecules or oxygen ends of water. They're only attached to a single one. They're attached to an H2O, and they're attracted to the lone pair of electrons on the oxygen, thereby creating a new molecule we'll look at in a little bit. Now, the Cls are surrounded as normal, but that just goes without saying. That's why the hydrogens are kind of highlighted here, is that hydrogens act differently. The hydrogens are what make it different. So a new phenomenon emerged. It turns out that something with HCl in it, like something with hydrogens in it, when the salt had hydrogen in it and it was added to solution and it separated out, and this new molecule was formed, we got new characteristics, new properties of the solution, different than other solutions. And so that was worth studying a little bit more. It's kind of a curious phenomenon. It seemed to be linked, though, to that presence of hydrogen ions. The fact that it brought hydrogen to the solution and separated it out, and the hydrogens were not surrounded, that seemed to be the reason why, because everything else with hydrogen, every other salt with hydrogen seemed to behave in a similar way, create a solution with properties similar. Okay, so it was linked to this hydrogen thing, and these extra properties were different than any other salt compound, and so they created all these different properties that we're going to dive into later. Okay, so H plus ions in the solution produce consistent, predictable, and scalable properties. These properties you could see them with other compounds. So they were consistent, they were predictable because they were made the same ones every time, and then they were scalable in that if you had more hydrogen concentration, that led to a greater amount of the characteristics. So like acids can burn your skin. If you have a more hydrogen concentration, it's a stronger acid. It can burn your skin even more at a higher concentration. Pretty wild how this turned out. Sidebar, what does a concentration mean? Thinking about the unit we just came out of, the most abundant type of concentration measurement is molarity. So of course that blank would be molarity. I don't fill it in except verbally. Nevertheless. So the hydrogen ion containing salts seem to proliferate these new curious properties or traits. When they dissociated in the solution, it created these new traits, namely in aqueous solutions. Aqueous, of course, means water is the solvent. Okay, what else might be capable of this was kind of the question on people's minds. Well, okay, if H-containing compounds do this, I wonder what else might do it. Turns out bases, salts in solution, bases also were discovered to have produced unique characteristics as well. And so this was worth discovering even further. So bases were kind of coupled with acids when their salts, acid salts and basic salts were put in solution. They provided these unique characteristics, and they were worth studying in greater detail. Though bases are other than and opposite of the properties of acids. So that's pretty interesting. And the question is, why? Why is our acids and bases in water solutions producing such new characteristics? Well, it turns out that acid and base salts disrupt the normal surround and dissolve technique that water normally behaves like. It disrupts it by making only one of the two separating components of the ion, either the anion or the cation, or excuse me, the anion or the cation, cation or the anion. Cation and the anion for you because it's reversed, I believe, from how you're seeing it from me. Anyway, that one of those only grabs onto one part of water and the other one is surrounded. So instead of both ions getting surrounded, only one of the ions gets surrounded, and the other one that's not surrounded kind of goes off and creates these manifest new features. So what we end up getting is that one part of the water's ionic nature is occupied or distracted, so to speak, and by surrounding, while the other part of the water's ionic nature, so one part of water is doing the surround of one of the ions, the other one is not occupied or whatever, it's liberated in another sense. Okay, so let's watch it in action. Remember, NaCl in water gets Na and Cl surrounded, and the way we can write that in shorthand is just put aqueous around each of the ions as written here. Now, it's written like a reaction only for clarity's sake. Ultimately, this is not a chemical reaction, it's a physical reaction, so just for reference there. That's how we can depict it to save time. Notice I still include water on the product side because water is there's so much of it. Well, the question I asked in class is why? How do we know that? Well, water's the solvent. So by definition, since water is the solvent, by definition, it is going to have way more of it remaining, even after it surrounds and dissolves a lot of the parts, a lot of the salts. So let's take a look here at acids. Let's take HCl, placed in water, breaks up into H plus and Cl minus, aqueous for both of those, plus excess water. But in this case, saying H plus aqueous is actually two reductions. We need more detail for it. Cl minus gets fully surrounded like normal, but the H, in fact, does not get surrounded, but only gets attached to an oxygen end of one water molecule. Instead of being surrounded by 3 or 4 or 6, it's only grabbed onto by one, which forms a molecule from H2O, grabs onto an H and becomes H3O plus. And the identity of that ion is called hydronium. H3O plus is called hydronium. You can find that on the back of your periodic table as well on the positive ion side. Anyway, so it turns out that this hydronium ion was the reason for all of what makes acidity or acids acidic. That's the reason. It's because the hydrogen in solution breaks apart, grabs onto a water molecule, but only one, and forms H3O plus, so that every free H that roams around produces an H3O plus. This is an interesting phenomenon. So now it's understood that H3O plus, called, do you remember? Hydronium, gives us the characteristic, or yields the characteristic acidic traits, which we'll look at later. Of course, H3O plus was caused ultimately because of the H plus ions being liberated in the solution. So the most common way we talk about acids, though, in acidity is in terms of the H plus ions. Because the hydrogen ions being separating out in the solution and being freed up in general is what makes it acidic. It's what turns into, it's what creates the H3O plus. It drives the process of H3O plus formation. We refer to acids in terms of H plus, but H plus, still keep in mind, the real reason for the acidity is because the H plus yields the production of, the formation of H3O plus. Okay, so hydronium is the driver of acidity, but in more practical terms, we end up discussing acidity in terms of H plus concentration, just because it's simpler, it's a little bit more shorthanded, and H plus creates the hydronium. Hydronium just ends up creating a little bit more of a clunky setup. So they're kind of interchangeable. We'll talk about them in both terms. If I say how much hydronium concentration is there out there, we're talking about also hydrogen ion concentration, and both of them equally discuss and mean some sort of acidic nature is at play. So do you get it? Take a moment, maybe rewind back if you need to. Make sure you understand, send me questions and whatnot. Bases, how do they look? Make sure you pause and look back if you need time. Of course, you can rewatch this video whenever. That's what's the beauty of videos. Okay, look at a base. This time the cation, the positive charge, gets surrounded in water. The OH separates out and leaves an excess of water. The OH this time actually gloms on to one of the hydrogens from an other water. Well, it separates into OH, but also the OH will grab onto a hydrogen part from another water, leaving more OH. So they end up just tossing around these excess OH ions, end up producing OH ions. They create this chain reaction of OH ions that are constantly being formed and unformed and formed and unformed, because the OH ions would grab an H from another water, leaving an OH for the other water. Then that would go find its own hydrogen and so on and so forth, leaving this abundance of OH ions for every NaOH that breaks apart. So every molar concentration of it causes more OH ions to be proliferated, and they can grab on hydrogens. And this process creates an abundance of OH, which gives us the basic characteristics. So it's a little bit less complicated. We end up getting not a surrounding situation, but this OH ion is roaming around freely. And the OH ion, called hydroxide, is the reason for the characterized prevalence of basic characteristics, basic properties, OH ions or hydroxide. What about the compounds that don't have hydroxide but still act like bases, like NH3, called ammonia? Ammonium is NH4 1 plus. NH3 is just ammonia. Find ammonium on the back of your periodic table as well. Bases, in comparison, like NH3, is still a base, even though it does not have an OH ion in it. It doesn't have the prevalence of it. We'll learn about definitions here in a minute, but as to what an acid and a base is. But the bottom line is NaOH is a base because it forms OH in water. NH3 is a base because it forms OH in water. Notice, NH3 actually will grab onto one of the hydrogens of waters nearby and produce NH4+, which then gets surrounded by some of the excess water, whereas leaving behind OH ions in its wake, which then repeat the same process that NaOH would do. It still acts like a base, even though NH3 is actually a non-polar, well, it's a polar covalent substance. It's a covalent substance, and somehow it's still acting like a base. So what makes a base is not just that it has OH in it, it's that it produces OH in water. It just tends to be that most of the bases have OH in them. So it's worthwhile taking a look at in greater detail. So next, do you get it? Think about it. If you have a level 0 or 1 understanding out of 2, a 0, 1, 2 is the rating I would give you that. If it's a 0, send me your questions. Go back and listen first, and then send me your questions. Got to make sure we understand this. How is acidity and basicity measured? pH. Of course, pH scale. Then I had students work on the scavenger hunt activity. Sorry. And that scavenger hunt activity, of course, has you answer 4 questions, give or take. And in those 4 questions, you would then find a neighbor or get up and ask a neighbor to see what if their 4 answers would help you fill in some of your blanks. And then you end up answering all of your blanks together. Gave students enough time to do that. And then we reconvened and we went over it. At the beginning of the next video, I'll actually go over some of those answers just for you to write. And I'm going to say them slowly and articulately, probably once or twice at a time in the next video at the beginning. And that way you can write them down at your own pace. Of course, that is the scavenger hunt portion of the worksheet. The right side part of the worksheet was this Bronsted-Lowry conjugate acids and bases. We're going to touch on that more in a moment. That's actually the beginning of day 2. So we're going to touch on that more in a moment. So just leave that one for a while. And you'll see these pages posted, of course, along with the video today, if they are not already. I believe they already are. Anyway, scavenger hunt, we're going to go over those answers. Beginning of the next video, look for it. Here it comes. So give students plenty of time to work on that. It's due tomorrow. I tell them more about strong and weak acids and bases. We'll talk more about that tomorrow as well. Essentially, strong acids or bases fully dissociate in water so that all the NaOH compounds produce only NAs and only OHs in water. No NaOH remains because it's a strong base. Compare that to, say, a weak acid or any weak acid or weak base, like acetic acid in water, only partially dissociates, so that some of the CH3COOHs produce their ion components and acid, but also some remain unseparated. That means they partially dissociate. We're going to look more of that in detail tomorrow or in the next video. So make sure you understand that, though. You can go and rewatch it. Of course, I also mentioned a neutralization reaction is where you have an acid and a base mixed together. They always produce the exact same products. Turns out it is basically a double replacement or double displacement reaction. So 1, 2, 2, 1, we can label them. And then that helps us match them up, HOH and NaCl. And it turns out no matter what, water and salt is always produced from neutralization reaction. Not table salt, a salt. This just happens to be table salt because of the 2 acids and bases involved. Another scenario, HCN, KOH, 2 different acids or a different acid and a different base, still produces water, and KCN, which is still a salt. Salt is just the street name, you could say, for an ionic compound. So what lies ahead? Acid and base characteristics that we're going to look at here in a moment. Definitions, that's going to be more of day 2. pH and POH calculations, that's sort of a day 2, day 3 hybrid. We just got finished with that on day 3 Monday, would be December 7th. And then we'll talk more about neutralizations and stuff there. And the concentration calculation using the log button is that pH, POH scenario. And that's sort of where I left students on at the end of day 1. Oh, wait, actually, there's one other thing we talk about on day 1. we actually go back to the slides a minute. Oops, sorry, let me get rid of my pen here. We actually go back to the slides, and I introduce this template for taking notes. I ask students to make this in their notes, and then we walk through a few of the slides that this covers. First, little prior knowledge. When you think about acids, what do you think? Danger, battery acid and corrosion, acid rain, acid burn, stomach acid maybe. When you think about bases, you might think about soap or cleaning materials, bleach, okay? And then I provide some definitions for acids and bases. Notice there are two definitions, and we need to really focus on both of those two, especially more in video 2. But notice that helps you fill out the definition part of your notes. Then I have students go through the notes themselves, go find them online, and fill out the portions that apply into the boxes of that note page. So go and do that now. Fill out that notes. That's the end of video 1. Send me your questions from the naming worksheet if you have it. Send me your questions from perhaps the conjugate or the scavenger hunt situation, and I'm about to go over those answers here at the beginning, at the beginning of the next video. But that concludes acid and bases day 1. So take a look at it. Let me know. Send me your questions. Let's communicate. Let's get things right. Thank you.